this is video 2 in the STEM or Chemistry Bootcamp, which really gets you ready so you're able to go in and take general chemistry or physics or biology and not have so many issues getting started in class. But anyway, today our focus is fairly simple. We want to talk about the powers of 10, how it relates to using the scientific notation and the metric system. And then I want to really focus on the metric system and kind of get you queued up to start using that a little bit. But before you proceed, stop this video, go get a writing utensil, paper, and a calculator so you're ready to go to work. So to understand the metric system, it's great to understand a pattern of tens. And I'm going to show you a small little video right now that will help you understand multiplying and dividing by 10 and how it sets a pattern with numbers. So what we're going to talk about today is a pattern with 10 that's going to help you understand both the metric system and scientific notation. And as you probably know, when you're using the standard system we use in the United States, the English system, it's not necessarily a set pattern. For example, if you're going from inches up to feet, there's 12 inches in a feet. Feet up to yards, there's 3 feet in every yard. So it's very inconsistent. So same sort of thing, 16 ounces in a pound. Maybe there's 2,000 pounds in a ton, depending on what kind of ton it is. So it's very confusing and it's inconsistent. So I'm going to show you kind of the beauty, just kind of the pattern of tens behind both the metric system and exponential notation. So let's start with 10. All right, if you think about what 10 is really 10 times 1. And if you talked about that in exponential notation like we talked about in the last video, you could say that's 10 raised to the power of 1. All right, great. So let's go out one more decimal. That's 100, which is 10 times 10 power 10 squared. If you keep growing, now you're up to 1,000. That's 10 times 10 times 10. So think about what we've done here. We moved our decimal over 1, 2, 3 times. You basically could say it's 10 cubed, right? So now we go up to 10,000. That's 10 times 10 times 10 times 10. Right? 1, 2, 3, 4. Move the decimal over. 1, 2, 3, 4. It would be 1 times 10 to the 4th power. Right? You keep going. 10 times 10 times 10, 5 times, right? It's 10 to the 5th. You can end up here with a good round figure just to get the point across here. 10 times 10. That is 10 to the 6. And so that's a million. And this is really important to know. Look, if it's to the second, it's 100. If it's to the 6, it's a million. And if you work your way down, look at how the patterns are going. 10 to the 6, all right? 1 with 6 zeros after it. 10 to the 5th, 1 with 5 zeros after it. 10 to the 4th, 1 with 4 zeros after it. 10 to the 3rd, 1 with 3 zeros after it. And so forth and so on. But if I kept going down on this pattern, I'd be left and say, okay, well, what if I took off the 1 0, didn't move the decimal at all? Anything raised to the 0 power is 1. Okay, so now what happens if I continue on with this pattern? Instead of multiplying by 10, I start dividing by 10. So I go down here and I say, okay, I'm going to take 1 and I'm going to divide it by 10. I would end up with 0.1. If I wanted to express that with exponential notation, it won't be 1 times 10 to the minus 1. And if I then decided to divide by 100, right, that would be 0.01 which if I express in decimal notation is 10 to the minus 2. And if I decided to divide by 1,000, right, that would be 0.001, which is 10 to the minus 3. And this could go on, and you could, if you were dividing by 1,000,000, it'd be 10 to the minus 6. By 1,000,000,000, 10 to the minus 9. So this is a very orderly and organized pattern. The nice thing is it isn't restrained to 1 times 10 to the 2. The idea that if I just increase by a factor of 10, I'm just moving the decimal over, that will apply to any number. Let me show you what I mean. Let's say that instead of 10 times 1, I was basically saying 10 times 5, which would be 50. All right? Which is the same thing as 10 times 1 times 5. Maybe I should put it this way. All right? Or if I went in here and said 10 times 10 times 5 again. Now I'd have 500. Now if I wanted to re-express this, and this is where the scientific notation comes into play, I would say, okay, I moved the decimal over once. I basically did 5 times 10. So you could express this 5 times 10 to the 1. You could express this one. Oh, that's 5 times 10 to the 2. And it doesn't matter what the number is. 10 times 10 times 10 times 6, for example. That would give me the number 6,000. 6 times 10 to the 3. And on and on and on. And this is how we get to scientific notation. So now with this background about the patterns of tens in place, we can talk about the metric system, which really does use this powers of 10 pattern. So the metric system is really all about prefixes that really tell you how big it is. So instead of using numbers, 10 to the second, for example, represents 100, or 10 to the third represents 1,000, or 10 to the sixth represents 1,000,000. It uses words to do the same thing. So if you look at the patterns out here, by using deca, you mean times 10. And using hecto, you mean times 100. Kilo means times 1,000, and mega means times 1,000,000. And if you're dividing, as opposed to 10 to the minus 2, for example, you would use centa, and that means 100th. Or milli means 1,000th, or micro means 1,000,000th. So now you're getting very small. All right, and if you divided by 1,000,000,000, you would be down to a nano. So the prefix in the metric system gives the power of 10. Now I want to take your attention to this right here, where there is no prefix. So what this is saying is if you see an abbreviation that has none of these prefixes associated with it, you are talking about the actual dimension. So that really is what I'm measuring, or the dimension that I'm measuring. And this is back to that table that I have you carrying around that hopefully you printed out from the last video, which basically says, look, for standard units, there's a dimension, for example, length. It has a unit of the meter, which is abbreviated M. If you had mass, that's a standard unit for how much stuff, which is measured with grams, and the abbreviation is a G. So when you see this G, there's no prefix associated. You're talking about 1 gram, about the size of a paperclip. That's that mass. But once you stack it with a prefix, now you're saying how many grams. And in this case, it's a kilogram, so that means there's 1,000. So that's the same thing as 10 to the 3 grams. So the K represents 10 to the 3, but the nice thing is it always represents 10 to the 3, always represents 1,000. Okay, by the same token, if you saw something like this where there's 2 M's associated, the first one's a prefix. It's telling you how small, that's milli. That's dividing by 1,000, 10 to the minus 3, right? And then the M is for meters, which if there were no prefix in front of it, right, that we know is a unit of length. And anyway, you could go on and look at these other dimensions. Time could do the same thing. It's a second, or the abbreviation S. So you could put an MS together and you'd have a millisecond. It's very small. Or you could have a KS together and you'd have a kilosecond. That's 1,000 seconds. So everything is done in powers of 10. It's very orderly. When you get into physics, you'll talk about a push or pull of matter, a force acting on something. That has a unit of a Newton, which is abbreviated M. In both physics and chemistry and biology, you talk about energy. It has a unit of joules, which is abbreviated with a J. So this is the metric system. So now let's focus here. And you'll notice that I have some of these prefixes, I have a little star up here. So what does that mean? That means that it's commonly used in STEM. So you don't memorize every one of these, because with practice, what we've found out is we've kind of pared it out to just a few that are used. So here's what I would like for you to memorize. Know what a kilo is. That's 1,000. And so now you can do a conversion that says, and we're going to just use mass for the example, there are 10 to the 3 grams in every kilogram. And here's my suggestion. Always write this in a matter so it's positive. And I'll show you what that means as we move on. So 10 to the 3 grams in a kilogram. The nice thing about the metric system, 10 to the 3 newtons in a kilonewton. 10 to the 3 seconds in a kilosecond. That conversion's in place. You should understand the mega, which is the big M. And pay attention, this is big M as opposed to little m for milli. Okay? There's 10 to the 6 grams in every megagram. Once again, I wrote this from the viewpoint of the smaller and kept it positive. I don't like to use negative exponents when I'm doing conversion factors. So here you have a centigram, for example, or in this case I'm using length or meters. So there's 10 to the 2 centimeters per meter. Now I could have also said there's 10 to the minus 2 meters per centimeter, but that sometimes can be a little confusing when you start doing conversions. And all right, here's the milli. There's 10 to the 3 milliliters per liter. I put that in terms of volume. Here's the micro. This shows up a lot in biology because a lot of times you add volumes in biology and microbiology that are in microliters. And there's 10 to the 6 microliters per liter. And look at this the little Greek symbol for micro. We're going to go ahead and show you nano as well. And that's because you hear a lot about nano things, right? There's 1 billion nanograms in every gram. So that I want you to print and memorize these conversions and work on those. And when you've done that, you can turn this video back on and I'll give you some practice problems. What about the conversion factors? Megaseconds to seconds. Now pay attention to this next problem. The conversion factor for milliseconds to seconds. And this is where it's really important that you pay attention to capitalization. And once again, because there's 2 letters involved, there's a prefix which gives the size, and then there's the regular unit abbreviation, which gives the dimension you're measuring. So in this case, I'm measuring time. And there you go, there's seconds again, so we're still dealing with time, but we're talking about microseconds. And the last conversion factor to practice on is meters to nanometers. All right, so stop your video and see if you can get all these answers, and then we'll give you the answer in the next slide. All right, so here's your answers. And the first thing that I would point out to you is I wrote them all in the positive form. By the way, to write it differently is not wrong. It's just a little inefficient. So this is true, that there are 10 to the minus 2 liters in every centiliter. That's true as well. It just can be problemsome. It's not wrong. It just generates some problems when you're doing dimensional analysis. So I always encourage my students to write it in the positive form. And you'll see why as we do this conversion section in the next video. Okay, number 2. There's 10 to the 2 centijoules in every joule. This is energy. Would it matter if I flip this over? Is it still true? There's 10 to the 2 centijoules per joule. That's true, and neither one of these is more correct. Okay, so I hope this has helped you understand the metric system and powers of 10. A lot of memorization in this video, but this is a good setup for doing conversions. So make sure you're very solid on doing those conversions for the starred units on your metric system table. Print it out. It's a good opportunity to use flashcards and get that down solid when you're ready and you're ready to move on, or you have that memorized and you're able to do this homework set on this video with a lot of confidence. Then you're ready to move on to video 3.